Okay, so an action potential is the transmission of a signal in nerve cells, and it's characterized by a depolarization and a quick repolarization. So really quick, I'm going to draw what a typical completed action potential looks like. I'll draw it a little bit bigger. So we know that our resting membrane potential is about -70, approximately -70. In order for an action potential to occur, it's all or nothing. So it's necessary to reach our threshold potential, TP for threshold potential, that'll be about -55 in the standard cell. In order to reach threshold potential, the cell has to experience EPSPs and IPSPs. Now it's important to reach threshold potential because we have to get past the axon hillock. In a nerve cell, that's going to be kind of like that part of the cell. And we have to be able to get to about -55 millivolts in order to get the signal to get past it. So EPSPs are excitatory post-synapse potentials, and IPSPs are inhibitory post-synaptic potentials. EPSPs are going to get us closer to threshold potential. So it's going to depolarize the cell a little bit. Depolarization will go that way, hyperpolarization will go this way. Now if we were to have an IPSP, we're actually going to hyperpolarize a little bit. And this is actually where graded potentials come in. Graded potentials are before action potentials happen, and graded potentials, they don't always result in an action potential. But if we have enough going on for our voltage to reach about -55, and sometimes it takes, multiple neurons firing onto one, or in a very extended charge to this neuron here, in order for us to reach this threshold potential. But once we reach our threshold potential, our cell is going to open up sodium voltage gated channels. Now these sodium voltage gated channels are going to allow sodium to rush into the cell. Now sodium, obviously there's a lot more on the outside of the cell, and this is going to allow it to rush into the cell. It's going to really quickly depolarize the cell. So we're going to actually get up to about +30 approximately millivolts when this happens. And this is the rising phase of our action potential. So once we get up here, we actually begin to start closing our sodium voltage gated channels because we don't need any. We've already fully depolarized the cell. And potassium channels at this point are open. So potassium will rush out of the cell. And that's actually going to allow us to get all the way back down to actually even past -70 millivolts. It'll typically take it down to around -90 millivolts. At this point, we're hyperpolarized. And in order to reach repolarization, we'll get back to our standard resting membrane potential. Leaky gated or leaky channels will open. That's going to allow sodium and potassium to go in and out of the cell as they need in order for the voltage to reach, our resting membrane potential again. So after, we're repolarizing, we have two periods. We have the absolute refractory period. The absolute refractory period is actually going to be a period of time where no matter what, no matter how much of these EPSPs we have, we can't get the cell to depolarize again. We're not going to have another action potential. Once we get past the absolute refractory period, we have another refractory period, and this is the relative the relative refractory period. The relative refractory period is actually a period of time where we're able to get another action potential off, but maybe we're down here. So obviously, in order for us to actually get another action potential, it's going to take a lot more of a stimulus to get us back to threshold potential so that we can reopen those voltage gated channels so that we can have another action potential. And then capacitance is how we determine the charge separated per volt. And we have time constant. Time constant is how long it takes to depolarize a section of a membrane. So as we have an action potential move down a cell, as it moves down the cell, there's going to be kind of all these sections, and as we depolarize one section, we depolarize the next, and we repolarize it. And so the time constant is just going to be how long it takes to repolarize that section of a membrane so that it's ready to have another action potential. The length constant is how far the charge has to travel away from that depolarized section so that we can have another action potential. And then the synapse is the space between one neuron and the next. There's chemical synapses, and then there's electrical synapses. And electrical synapses are joined, but chemical synapses have a little bit of space between them. So this is our synapse. And in order for us to get this signal across with a chemical synapse, we're going to have all these vesicles, kind of like bubbles, filled with hormones or neurotransmitters or whatever. We're going to have these snare proteins along the end of this synapse. Now these snare proteins are going to grab onto these vesicles. They're going to pull them in towards the synapse. Once the vesicles reach the edge of the synapse, they'll actually dump their contents into the synapse, where we're going to have receptors that pick up those neurotransmitters and move the signal to the next neuron.